Hello everyone, my name is Chandan Bose. I'm currently a postdoctoral fellow at the University of Liège, Belgium. Today, I'm going to talk about the environmental modules, which is a useful tool for the CFD workflow in an HPC system. I thank the organizing committee of this HPC workshop for inviting me to deliver this tutorial talk. Before going into the main topic, let me first introduce myself. I work at the Fluid Structure Interaction and Experimental Aerodynamics Laboratory with Professor Grigorios Dimitriadis, and my research broadly focuses on the fluid structure interaction and nonlinear aeroelasticity problem, and the primary objective is to integrate the high fidelity CFD simulations with the experiments carried out in our lab in order to validate the experimental results. Let me give you an outline of the present talk. I have divided the content of this talk into two sections. In the first section, I will talk about the overview of the HPC facilities that I use in Belgium and UK, and I will get you started with the basic uses of a HPC cluster. I will also talk about the basic CFD workflow in HPC system. The second section is about modules. There I will talk about what are environmental modules and why they are needed, how to effectively use them, and I will also introduce to the important tool chains such as EasyBuild and FOSS, which is free and open source software. In Belgium, we have two different broad supercomputing systems. One is dedicated to the Flanders region, which is Dutch speaking, which is VSC, and the other, which we use in the University of Liège, is CESI, which is dedicated to the Wallonia region. Under this CESI consortium, we have different tier 2 HPC clusters, and they are situated in 5 different universities, and I am located here in the University of Liège, where we have the HPC cluster NIC4, which we normally use for our research work. However, we can log into any of these 5 HPC systems to simulate our CFD cases. So just to give an overview, this NIC4 cluster is very much suitable for massively parallel jobs, and it is having 2048 CPUs with 64 GB RAM per node, and we also have Hercules 2, Dragon 2, Lemaitre 3 and Dragon 1 clusters, which are currently in the mode of upgradation to the most recent configuration. The second HPC system that I use belongs to the UK National Supercomputing Service Archer, and as part of our EPSRC project, I have access to the tier 2 facility Cyrus, which has 280 standard compute nodes and 2 GPU nodes, and a Cyrus standard compute node contains 2.1 GHz 18 core and 2 threads per core Intel Xeon processor and 256 GB of memory shared between 2 processors. Let us first see what are the different components or different steps in the CFD workflow when we perform the CFD simulations in the HPC. So the first thing is you have to be connected with internet, and then you have to have a secure cell protocol to get connected with the cluster. So I will demonstrate how to do that. Once you are connected to the cluster, you are in the login node, and then you have to use a job scheduler to batch your job and submit. After you submit your job, it will be in a queue, and when your job will be running, this job will be performed by some of the compute nodes. And once the job is run and you have the results, those results will be stored in the storage. So mostly in any HPC system, we have 2 different kinds of storage. One is the global long-term storage, where there will be a quota. And the second one is the global scratch storage, which normally give you huge amount of space to locally store your data and run your cases. However, there will be a time limit after which those data will be automatically deleted. However, all these basic configurations and policies varies from one cluster to another. Now, the first step So before we do anything, we have to get connected to the HPC system, which is done by the Secure Shell Protocol, SSH. And mostly Open SSH is used in case of Linux and Mac operating systems. And for Windows, we have different open source and free third-party libraries through which we can use this secure shell protocol, such as Windows PowerShell or Windows Subsystem Linux, which is available for Windows 10. We have MobaXterm, we have Git Bash, and we have PuTTY, which are most popularly used. So OpenSSH allows using preset configurations. In some cases, as I will demonstrate, additional gateways are given for particular universities to create a double layer protection against the cyber crimes. So normally the easiest use of this secure shell protocol is that you have to use the command SSH, and then you have to give your username at the host name of the cluster. And also it is possible to avoid this repetitive step of giving your username and host name by configuring a preset in the SSH directory, so that you can directly log into the cluster by giving a short keyword or the name of the cluster. And here the -X denotes to the X server, which is mostly used for graphical interfaces for SSH. So you can see here that without giving the user and host name, by just giving a short keyword, which is the name of the cluster, I can do SSH NIC4 and I can get immediately logged into the system, which actually needs a preset SSH configuration, and I will show you how to do that. So for that, we have to create a config file in the SSH directory at home, which looks like this. Popularly used job schedulers are Slum and OpenPBS. The task of job scheduler is to allocate resources to a particular job based on the requested number of processors and nodes and the simulation time, and also the priority of that particular user. By the way, Slum is the name of a popular energy drink. From these distributions of the user throughout the world, it can be seen that Slum is used by most of the users, almost 26% of all the HPC systems throughout the world. These job schedulers work based on different algorithms, such as first come first serve, shortest job first, backfilling, which I will describe in a while, and also fair share for any particular HPC user. There are different comments for submitting a job, queuing a job, canceling a job, and seeing the accounting details of the all past jobs for particular job scheduler. So these are some of the comments shown here for Slum as well as OpenPBS. And also there is a comment called quota to see the allocated storage and how much is yet available for any particular user. And also we can use SCP to securely copy the files from a cluster to our local storage, or from a local folder to the particular cluster. So this is an example of a typical job script used by the Slum scheduler. It is a shell script or bash script, and these are the regular bash commands. And it is to be noted that these comments starting with sbatch are considered as comments by bash. However, Slum takes them as parameters, and no bash variables are allowed in this portion. So the first line prescribes the job name, then the output file name, and then number of processors needed for the job, and the memory required per CPU, and also the required time for the simulation. Now, let me briefly talk about the intelligent choice of resources while running a job in HPC. In this schematic, we can see that there are 3 jobs already running in a HPC system, and the x-axis is time and the y-axis is the resources requested. And these numbers in each of these jobs are the priority, which enables the job scheduler to decide which job should be started first. If we assume that there are 2 more jobs submitted, one with a 90 priority, assume that 90% priority, and the other is with 10 priority. Obviously, the 90 priority job will get started first. Now you can see that there is a vacancy of resources before this job of 90. But the second job with 10 priority cannot fit in that because the resources requested is higher. There comes the concept of backfilling. If we intelligently request by increasing the time and reducing the resources requested, you can see that this changed version of the job can easily fit into the vacancy that is already available before this job with 90 priority. Then the scheduler will try to schedule this job soon because it will try to backfill the resources which are vacant even before this job with 90 priority. So in this way, we can reduce the wall time of our jobs with even lower priority. Now, let us look into the basic CFD workflow in HPC. As I have already explained that basic workflow in the HPC looks like this. Now, while we do CFD simulations in HPC, the CFD workflow looks like this, and which fits into the compute nodes. So it consists of the pre-processing part, which involves geometry preparation and the meshing, and then the solution part, which involves different solvers, and particularly this is the area that we need to stress because this is the most time consuming part and which may need parallel processing, and then the post-processing part comes. Now let me get you started with the HPC system and show you how to create a job script for CFD simulation with the installed CFD softwares in the clusters. So you can see this terminal and you can see that I am already logged into the NIC4 clusters, where this is my username CBOS and nic4.login is the host name. To demonstrate how to log into the cluster through SSH, let me log out first. And you can see that connection to NIC4 is closed. Let me show you how to log in. So in this NIC4 cluster, I would simply log in by using the SSH command and giving a keyword which is the name of the cluster NIC4, and it will ask for the private passphrase for me, and for a double layer protection it will ask for second time. And now I am logged in. So to show you how we can create this preset configuration so that we do not have to use our username and the host name again and again, I will again log out of this system, and you can see that I am now in my workstation and I can see the path that I am in the home Chandan, which is the Linux workstation home directory path. And now let me show you where my SSH configuration file is located. It is located in the .ssh folder, and if I see the files, I can see that I have a config file here. So let me use a nano text editor to see the content of that config file. And here is the content of the config file. So you can see that the first portion of the config file is the ULEH gateway, which allows me to be identified as a ULEH user, and the identity file is the idrsa.sesi, which is shared with the sesi cluster. And then I give the keywords for all these different HPC clusters, and I actually define my username and give the host names for each of these HPC clusters. So that allows me to simply log in by the SSH command and the keyword of any particular cluster. Now let's see, I want to log into Hercules instead of NIC4. As you can see that for Hercules, the name is Hercules, the keyword is Hercules, and I have defined the host name as hercules.ptci unamur.be, which is located in University of Namur. So I will simply do SSH Hercules, and it will ask again the passphrase, and I have to give it for the second time. And now you can see that I am logged into Hercules. So it is a very efficient way of logging into different HPC clusters without giving the normal SSH command, which is SSH username @ hostname. Now, if we see in this SSH folder, we see that I have the SSH keys, both public and private keys, which are shared with the HPC system to allow me to log in to those HPC systems through the secure shell protocol. Now, let me show you how do we log in to the Cyrus of UK. So here you can see that I am already logged into the Cyrus login node, and to show you how to log in again, I will log out of it, and you can see that now the connection is closed and I am again in my Linux workstation. So I will simply use SSH cbos1 @ login.cyrus.ac.uk. In this case, I am not using any preset configuration file, but I'm directly mentioning my username and the host name through the SSH protocol, and which will again ask me the password, and I'm logged into this, and which will show me that welcome to Cyrus, and documentation and websites are this. Now, let me show you the basic configuration of the NIC4 cluster. To do that, I will see the file CPU info, and it will give me the complete details of the computing nodes of the NIC4 cluster. So if we go to the top, I can see that the computing node is Intel Xeon CPU ES2650 @ 2 GHz processor. And we can get all the detailed information of the hardware of different compute nodes by this. The other way to know the basic configuration of the cluster is by doing sinfo, which will show us the current status of all the computing nodes and the hardware type of divisions of the computing nodes. So you can see that in NIC4 we have only one partition, which is called devq, and all are up. That means we can run in all these computing nodes, and for each of these, how many nodes are available and what is the current state, what are the node numbers for these particular partitions. Next, let me show you what are the environmental variables. As I already mentioned, the basic environmental variable is $home. So all these environmental variables can be echoed by using a dollar symbol. If I use echo $home, it will show me the path which is assigned to this environment variable home. So if I want to go to that particular path, I can directly give cd $home, and I am already in the home directory. That's why there is no change, and I can see that by using the current path, right? So the next environmental variable is environment by env, which will show you all the basic environmental configuration for this particular cell session. So this is only valid for this particular terminal. There are plenty, but there are some important environmental variables such as cpath of Slum, module version, path is another important environmental variable. This is another important environmental variable which I'll show, LD library path and cluster name, etc. So the important thing is that if I close this terminal and open a new one, some of these environmental settings will be changed. So now let us look into the environmental variable path. So if I echo path, I will see that this contains the paths for all important binary files which are already available. So this is very important because if you want to use any software, the binary file path should be included into this path environmental variable. Similarly, LD library path shows the path for the library folders for all the available softwares. Some of the other important environmental variables in this NIC4 clusters are SSH home. So if I echo the path for SSH home, it will show me a different path because SSH home is a directory which is centrally linked to all the SSH clusters. So if I create a file in SSH home, this file will be available from any of the clusters which are under the SSH consortium. The other important environmental variables are the scratch, which is the local scratch for this NIC4 cluster, and the other one is global scratch, which is a global scratch folder accessible from any of the SSH clusters. So if we create a job script in the global scratch, I can submit that job from any of these SSH clusters. Now let me show you how to create a job script for a CFD simulation and submit that using Slum and monitor whether it is running and whether it is pending and how to use other Slum comments. So for that, let me go to the global scratch folder where my job folder is located. And if I see the contents for this folder, I can see that all my case folders are located here. And I have created a folder for demonstrating this called HPC IITM. So let me go to this folder, and within that, I have a folder called tutorial. Where I have the files for a CFD case of a pitching airfoil. So if you are aware of the OpenFOAM CFD cases, you can understand that I have the needed zero, constant and system folder, and I have a job script which I have already demonstrated. It is a bash script and it is needed to submit the job. So let us first see what is written in this job script. So as I already explained, it is a bash script which has all these SPatch commands which will be read by Slum as input, and I have given a job name of pitching case, and the output will be pitching case.txt. And I have requested 16 processor within one node. So the processors per node is 16 and 48 hours for the simulation time. And I have requested memory per CPU as 1000, so 1 GB around. And I have also included options for getting notifications in my mail ID. And here are the required softwares for running this job, which I will come in a later part of the talk. And this is also a required comment for sourcing the BASRC for OpenFOAM software. And this is a parallel job. As you can see that the total domain will be decomposed into 16 processor. So I am using MPI run, which is using OpenMPI to run my executable with 16 processors, and the outputs are getting stored in this log file. Let me first check that if I have already any cases in queue. So to do that, I have to do SQ minus U, which is, or hyphen U for user, and my username is CBOS. And I can see that I don't have any cases pending or running already. So this comment is used to monitor the cases which you have already submitted using Slum. So now let me submit this particular CFD case in HPC. For that, I will use sbatch comment. Sbatch and the script name is script underscore pimplefoam.sh. As I submit, Slum gives me a job ID, which is 2220754, which is needed for further monitoring or cancelling in future. Now, if I do the same, if I do SQ minus UCBOS, I will see that I have a job which is with job ID 2220754, and it is running in the dev queue partition. Name is a case name, and the status is PD, which means pending, and it needs one node and it is in priority. Now, if I don't want this job, I want to cancel it, I have to use it as cancel and the job ID 2220754. And now if I do SQ again, I will see that the job with this job ID has been cancelled. If I want to get the accounting information for the cases already run in my account, I have to use sact. So if I give sact, it will show that recently I have submitted 2 jobs with 2 job IDs and they are cancelled and they have not run and there were no allocated CPUs for them. However, it will only show you the recent jobs. If I want to show the history of all the cases I have run in the past from a starting date, I have to use an additional argument for sact, and that is let's say I want to know from 1st of May 2020 and I want to know how many cases have been run in my account. Then it will show the details of all the cases and their status, failed, completed, and everything, how many processors were allocated, everything from the starting date of 1st May 2020. 2 basic questions that comes up is, first question is how to set the environment for running the pre-installed CFD softwares, because this pre-installed CFD softwares require appropriate environment to be set up. And the second question comes as how to compile open source CFD libraries. Often it's said people need to be able to install your software before they can use it. There is obviously a gap between the software developers and the software users, and sometimes this can be really frustrating, time consuming and messy. The software developers care a little about it, and especially when they are scientific researchers who are not expert in the domain of software development. Here comes the usefulness of modules. What are modules? Environmental modules is a system for dynamically loading software packages into your environment. They are often used in HPC systems for efficiently managing the cell environment needed by different software packages. They allow multiple versions of the same software to coexist on the system together. And normally, a Lua-based environmental module system is popularly used in many HPC systems. I will demonstrate why these modules are really needed. HPC systems are often stacked with lots of different softwares with different versions, as you can see. However, while using our own compiled libraries or using any pre-installed CFD software, we need particular versions of these dependent libraries. Sometimes it becomes very difficult to select particular versions of these environment libraries or the dependency libraries in the absence of modules. So let us assume that we have lot of softwares in the software stack of a HPC system. On the other hand, we have hardware, operating system, cell, and we need a working environment for running a particular software. And for that, we need a particular dependent environment of appropriate versions of appropriate softwares. So there comes modules, which helps us to choose the proper version of these softwares and load them before running the desired software like this. So now we have a complete workflow where I have hardware, operating system, cell, and a background environment where I have appropriate versions of appropriate softwares. This workflow will be demonstrated soon by a hands-on session. So for the effective use of modules, we have a series of module commands, which I will demonstrate one by one and show how to use them to effectively manage your background environment and to build your own software from source code. Now, let me demonstrate you how to use modules. Before that, let us first see what are the different software stacks that are already installed in the HPC cluster. For example, I'm now logged into NIC4, and let us see what are the different softwares that are already installed in this cluster. I will describe what is this comment in a while. So you can see now that these are the different softwares which are already installed currently in the NIC4 cluster. So we can see some of them are already in the local modules such as OpenMPI, some older versions, and CMake, which is a GNU compiler. It is to be noted that there are so many CMake versions are installed. So this is the basic purpose of modules, that it allows using different version of the same software. So if we come again for GCC, we can see that from GCC 4.8.1 to the very latest version GCC 9.2.0 is also installed. Similarly, another important capability is OpenMPI. So if we look at this, we can see OpenMPI 1.6.4 built upon GCC 4.8.1. 2, we can have OpenMPI 1.8.4 built upon GCC 4.9.2. So these are the main points to be noted, that we have so many versions of the same softwares which are very much confusing when we try to build some software from sources. So here comes modules which helps us choosing the correct software or correct environment library with correct version as needed by our source code. For the sake of completeness, I will also show what are the software stacks already installed in this Cyrus HPC cluster. So similar to NIC4, you can see starting from the commercial software ANSYS with different versions 17.2, 18, 19, 19.2, 2020 R1, and the open source software such as OpenFOAM version 8.0, OpenFOAM version 9.12, and also the OpenMPI different versions, Intel compilers, GCC different versions. Everything is already installed for the ease of use. Now, how to manage this software stack? There comes modules. Let us now see the different module capabilities which will help us to manage the software stack and choose the appropriate version of the required softwares for building new softwares from sources, as well as for running softwares with appropriate environment. So the first module command comes as module avail, which I have already used. This shows the availability of all the pre-installed softwares in this cluster. These softwares are pre-installed in this cluster. That does not guarantee that these softwares are available to us at this stage. So to know what are the softwares that are available to us at this stage to use, we have to use the command module list. So you can see that among all those pre-installed softwares, we only have two software libraries. One is shared. Within shared, we have many softwares, and we have Slum. And the question is, why these two are there when we are starting a terminal? So for that, we have to go to the system basrc file. So now let us open the system basrc. Towards the end of this system basrc, we can see among all these comments, we can see this line, module load, shared, and slum. So this is the reason that when we are sourcing the basrc by opening a new terminal, these two software libraries are already getting loaded. So if we want to load any modules automatically when we start a bash shell, we have to add them into the system basrc file. However, that is not always suggested, because in different session we might need different environment based on the software that we are going to build or we are going to use, which is pre-installed. So module list gives us the available softwares for use at this stage. Now, if we want to add more softwares to this list, we have to know which version we want to load. So for example, let us assume that I want a GNU compiler, GCC, and a MPI, message passing interface, which is OpenMPI. So I want to load the recent version of these two softwares for building a source code. How to know that which versions are available? One way is, as I already explained, that you do module available, but then you get all the lists, and among that you have to find out what are the version available for this particular softwares, which sometimes gets messy in the terminal. So for that, let us use module avail GCC. So this is much cleaner. It gives us that these are the versions of GCC that is available for loading, right? So similarly, if I use module available open MPI, so these are the version available for loading. Please note that here these OpenMPI versions are loaded for particular GCC versions. So they are built upon this particular GCC version. So if we want to use a particular OpenMPI, we have to load that version of GCC, right? So for example, if we want to load GCC version 4.9.2, we have to simply do module load GCC 4.9. Okay. Now, if we do module list, I can see that along with shared and slum, I have now GCC 4.9.2, and it has automatically loaded another software GDB 7.8.1, which is a dependency to this GCC. Now, if I want to load module load OpenMPI, which is based on some other GCC, let's say 4.81. So I want to load OpenMPI 1.8.4 built upon GCC 4.8.1. 1.8.4 built upon GCC 4.8.1, which is not the loaded GCC version. Then what happens? It shows us that GCC 4.8.1 error, module GCC 4.8.1 conflicts with the currently loaded module GCC 4.9.2. So now that's not the appropriate version of OpenMPI that we need, because then based on this OpenMPI and this GCC compiler, you cannot compile your source code. It will throw some errors. So how to get rid of this? We have to unload this wrong OpenMPI version and then load the correct OpenMPI version again. So let us do module unload OpenMPI 1.8.4 built upon GCC 4.8.1. So now I have unloaded this OpenMPI version. So to check whether this OpenMPI version it's still there or not, we will again do module list, and we see that we have shared, slum, and GCC 4.9.2. The OpenMPI version is not there. So now I have to load the correct OpenMPI version. So let us load, let us again see what are the available OpenMPI versions, and corresponding to GCC 4.9.2, I see OpenMPI 1.8.4, GCC 4.9.2. So let us now load this version. So module load OpenMPI 1.8.4 built upon GCC 4.9.2. Now it is seen that it does not throw any error and it is properly loaded. So now if I do module list again, I can see that now I have OpenMPI, GCC, both, which are compatible to each other. Now I can easily use them to compile any source code. So till now we have seen how to see the available software's versions for loading, how to load them, how to unload them if it is not compatible, and how to choose the proper version. Suppose I want to immediately know what version of GCC I already have. So for that we will do which GCC. It will show that GCC 4.9.2 is already loaded in our environment, and this is the path to the binary file. So this is very important. Similarly, if I do which OpenMPI, it shows me that no OpenMPI. That's correct, because OpenMPI is not the binary file. So the binary file is located as MPI run. That's why there is no OpenMPI. So it could not find the binary file for OpenMPI, although OpenMPI is loaded in the environment. So for that, we have to do which MPI run. Now it shows that MPI run binary file is located as OpenMPI 1.8.4 and GCC 4.9.2, and this is the path for binary file. These paths are very important because when you want to compile your source code using some utility such as CMake, you have to mention these paths to the binary files so that it can find easily, because sometimes it is very difficult to find the path of appropriate binaries which are compatible to our source code. That's where we can use modules effectively to find this path. To get more into this, if I want to know where the library files of this GCC software is located, so for that the module command is module show GCC 4.9.2, which is already loaded. So this shows us that is dependent on this library. So when you load GCC 4.9.2, this module is already loaded. Now this is the binary file path which is included in the path, system path, as I have already shown. And this is the library path which is linked to LD library path, which is very important. So now if we echo path, we can see that all these loaded module libraries binary files are added in the path. So let us now look into the GCC binary. Where is that? So you can see that the CM shared apps GDB 7.8.1 binary and CM shared apps GCC 4.9.2 binary. These two binary paths are already loaded into the system path, system environment path automatically by modules. So this is very important. Otherwise, if these paths are not mentioned in the system path, then we cannot use these softwares. Similarly, if we echo LD library path, we can see that CM shared apps GCC 4.9.2 library and library 64 files are already added to the system LD library path. Modules helps us by keeping track of the loaded softwares and their particular versions so that we can effectively use them while running any pre-installed software or building any software from source. So now the other module commands that are very important is that if we do module list, we'll see that now these are the loaded softwares in my environment. Now, if I don't want any of this, I will do module purge. And then now if we do module list, I see that no module files are currently loaded for this particular bash session. If I open a new bash session, my bash RC is again sourced and the module files that are already mentioned in the bash RC file will be loaded. So this is one very important utility which helps us getting rid of unnecessary module files. Another interesting module command is module swap, by which you can switch between different versions of solver. To demonstrate that, let us first see what are the modules available. So by doing module list, we see that these are the different modules are already there, and note that I am inside a super cluster now. And let us first see if we have any GCC compiler already available. So by doing with GCC, I see that there is no GCC loaded. So now let us see what are the versions available here. Module avail GCC, we see that 3 GCC versions are available: GCC 6.2.0, GCC 6.3.0, and GCC 8.2.0. So let us now load module GCC 6.2.0. Okay, now by doing module list, I see that I have GCC 6.2.0 module loaded in the environment. So now if I want this GCC version of 6.2.0 swap by the version of 8.2.0, let us now do module swap or module switch GCC 6.2.0 by GCC 8.2.0. So now if I do module list, I see that I have GCC 8.2.0 instead of 6.2.0. Note that this module switch is sometimes also used as module swap depending on the different module version. So there we should do module swap, the same thing, but in this module version module switch is used. So how to know what is the module version? To know that, we can do module help, and there I can see the module version is modules release 4.1.4, and also you can see all the associated commands. You can see here switch and swap both are used in this case, and these are all the associated module commands that can be used. Now doing reset. So the final important capability of modules are creating module collections. Now let us assume that for installing or compiling any source code or any open source softwares, I need a set of modules to be there. Or let us consider that while running a pre-installed software, I need a particular environment which should consist of certain versions of modules of some libraries such as GCC or OpenMPI. Doing module list, I see that I have GCC 8.2.0. So let us now load another module of OpenMPI. So by doing module avail OpenMPI, we see that corresponding to GCC 8.2.0 or GCC 8, we have this OpenMPI version 4.0.3. So let us load that OpenMPI GCC 8. Now doing module list, we have both OpenMPI 4.0.3 built upon GCC 8 and GCC 8.2.0. Now let us consider that this is the set of module softwares needed for a particular installation of a software or running of any pre-installed software. So I want to save this collection as my module. So to do that, we have to use module save, and we have to give a name to this collection. Let's say my modules. That's it. So this collection is saved. How to see that particular collection? We have to do module save list, and we can see that named collection list my modules. Let us assume that we are in a new setting and we do not have this previous collection loaded, and I really need the same environment as before. So if we see that in module list, we have the existing modules which are automatically loaded from the basrc, but we do not have any GCC or OpenMPI. Now, for my purpose, I need the exact same versions of GCC and OpenMPI as before. So we can load my previous collection. So if we see module save list, we can see that I have that collection saved as my modules, and now we have to load this collection. So for that, we'll use module restore my modules, and now if I do module list, I can see that exactly the same version of GCC and OpenMPI are loaded and we are set to go. So this is a very useful command of module by which we can actually save the exact same environment setting for particular jobs. So for example, when you submit a script to run a OpenFOAM case, you need a particular environment. So if you remember, I showed you that in the previous script, I had two particular software stacks to be loaded by module load commands. Now, instead of, I could use a module collection of all those modules creating a particular environment, and I could just give this command in my script as module restore my modules, or the name of that module collection, which could have loaded the exact same environment setting for running of that software. So that is the usefulness of module collections. Now I'm back to the NIC4 cluster, and now let me show you the important tool chains available in this cluster. So two important tool chains that we often need. One is easy build, the other is free and open source software, and the other being Intel toolchain, which I do not use often. So if I do module load easy build, you can see that easy build is loaded. Now if I do module available FOSS, which is free and open source software, you can see that I have FOSS starting from 2019B, which is the most recent installed in this cluster, and having up to 2015A. Each of these FOSS releases, where A and B are the biannual releases, contain different stacks of tools or different software chains. So according to the compatibility, I can load whichever I need. So now if I do module list, I can see that I have GCC 4.9.2, OpenMPI 1.8.4 based on GCC 4.9.2, and easy build. I do not have any other softwares loaded. So now let us also unload this GCC version and OpenMPI version for the sake of demonstration. So module unload GCC and module unload OpenMPI. So now again see by module list that I have easy build only, no other software leads. Now let us load the free and open source software toolchain by module load FOSS 2019B, and this is loaded as a toolchain. Interestingly, if we do now module list, we see that all the software libraries included in this toolchains are automatically loaded. So we do not have to worry about loading each of them separately. That's the beauty of this free and open source softwares. So it includes GCC 8.3. It already has OpenMPI 3.1.4 based on GCC 8.3, which are most recent. And it has also GCC Core 8.3.0 and JEDLib. It has FFTW, it has OpenBlast, it has Calapack, etc. So it has most of the needed common dependencies that I have already shown. And if something is not included in this, we have to separately load them or separately build them using these modules. And with that, I thank you all for your patience, and I hope you have liked this talk. And now I am open to any question if you may have.